Before we start the next example, just want to have a quick reminder of what we remember about the product rule. So this next example requires combining the product rule with the chain rule. So you have some examples like that in your 3.6 textbook work. But we want to see what it looks like here when I'm taking the derivative of a function of y with respect to x. So just for a second, there we go. I want to take the derivative with respect to x of x times y. So I'm going to have to use the chain rule. This is going to be the first times the derivative of the second, so the derivative with respect to x of y, plus the second, which is y, times the derivative with respect to x of the first. And in this case, the first is the x. So just notice that when I take the derivative with respect to x of x times y, I have to use both the chain rule and the product rule. X times, here I'm going to simplify this part, x times the derivative of x, the derivative with respect to x of y, that's x times the derivative with respect to x of y is just dy dx. And then here, plus y times the derivative with respect to x of x. Well, the derivative with respect to x of x is just 1, so you're going to see in the next example, I'm going to have to take the derivative of x times y with respect to x, and I'm going to get x dy dx plus y as the result. I have another example here. This is the third example on your paper. I want to find the equation of the tangent line to some curve. And I have no guarantee that this is a function. It's some kind of curve that I only have a description that looks like an equation, and I can't seem to isolate y. I can still find the slope by finding dy dx. And to do that, when I can't get y by itself, I use implicit differentiation. So I'm going to take the derivative of both sides of this equation with respect to x. I'll end up with dy dx as a variable in my equation, and I'm going to isolate the dy dx. So here we go. I'm going to start with this equation here. X squared minus xy plus y squared equals 7. Take the derivative of every single term in this equation with respect to x. So the easy parts, the derivative of x squared with respect to x is just 2x. On the other side of the equal sign, the derivative with respect to x of 7 is just 0. So we get two other parts we have to think about. I want to subtract, you can see I've used a subtraction sign here, the derivative with respect to x of x times y. Well, this is why we took a minute just at the beginning of this video to remember that if we want to take the derivative of two things multiplied together, we have to use the product rule. And in this case, it's the product rule combined with the chain rule. So a common error here would be to not distribute that subtraction. So that's why I've put the product rule I'm going to get, the product rule result I'm going to get inside these big brackets. So I'm going to hide that subtraction sign for a second and pretend I'm just taking the derivative of xy with respect to x. Well, that's the first times the derivative of the second plus the second times the derivative of the first. Notice that the first is just x, so its derivative is just 1, which is why I don't see derivative of the first anywhere in this work. And then here, I want to take the derivative of y squared with respect to x. Well, the derivative of y squared with respect to x is the derivative of y squared with respect to y, which is 2y, times the derivative of y with respect to x, which we just call dy dx. My next job here is to simplify and distribute that subtraction over those big brackets. I have 2x minus x times dy dx minus a y plus 2y times dy dx equals 0 on the right-hand side. Remember, the whole goal here was to find dy dx, which is going to give us the slope of the tangent line. So my goal, what I'm trying to do, is to isolate that dy dx expression. Well, the problem right now is I see dy dx in more than one place. You can't isolate something that shows up in two different places. So my first job is to move everything with a dy dx term over to the left, and move everything that doesn't have a dy dx factor in it over to the right-hand side of the equal sign. So the fastest way to do that is to subtract 2x from both sides, and then to undo the minus y, I'm going to add y to both sides. So here's my new equation. And notice that on the left, I would have had 2y dy dx minus x dy dx. The whole point is to get dy dx into one place. The way to do that is to factor the dy dx out. So you can see what I have here. And then I have just one more step. I'm trying to get dy dx by himself. So I'm going to divide both sides by 2y minus x. And that's the answer you see here. So that's a formula for the slope of the line tangent anywhere on this curve, at least anywhere that that slope exists. So our next job, we're going to find the actual slope at the point we've been given. We've been given an x-coordinate of -1 and a y-coordinate of 2. There we go. So we're going to plug those values in for the x and the y, and we get a slope of 4/5. Once we have that, we have the ordered pair, we have the slope. We're just going to write the tangent line equation. So here, y minus 2 is 4/5, x plus 1. Remember, when you take the AP test, you have no obligation to simplify that. If you left that answer on my test, that would get full credit. And then how do we find the equation of the normal line? We're going to use the same ordered pair, but the opposite reciprocal. Normal means perpendicular, so we want the slopes to be perpendicular. The opposite reciprocal of 4/5, -5/4. And we get this normal line equation here.